Good morning, everyone. Welcome to my talk on machine learning. I see the room is full, even more full than expected. People are sitting on the ground. I hope you're comfortable for the next 45 minutes. It doesn't happen too often, so I'm actually excited about this. So I will do a talk on building a recommender system using Apache Spark and a little bit of Akka to show you how you can integrate this into your existing software using what other people would call microservices. I'm going to call them services. Microservices, I did this because that will get me into the conference. Please, if you like my session, leave a rating. If you don't, leave a rating as well and tell me why. I need this information because I want to get better at this. I want to learn from you what you like, what you didn't like. If you'd like to talk to me personally, I will be around the conference this afternoon still, so you can find me behind this laptop with a large amount of stickers on it. So let's talk about a little bit about recommendation systems and what they do today for us. Who here is using Netflix at the moment? Who has a subscription? Well, not a, yeah, typical at the moment. Watching a movie instead of watching me talk, okay. Who has a subscription in Spotify? Cool. What do we think of the recommendations of Netflix? How are they doing on the homepage? It's okay. He's saying bad. It's okay. They suck, basically, yeah. I'm going to show you today why they suck. And why I'm not doing any better, by the way. So recommendations is, if you've used Google before, we all have done that. You're basically searching for stuff you know is there. If you search for Scala, you will find stuff with Scala, because you know there should be something there. And it's a one-on-one match with your search query. So what do recommendations do for you then? Recommendations are items that you don't know exist, but the computer knows. And the computer knows you, and so he's capable of showing you those items. And you may or may not like them, because Netflix does this as well with movies. And some people will say it sucks, some people will say it's okay, other people are more or less convinced that it absolutely sucks. So and that's also one of the things I'd like to tell you up front about machine learning in general. Machine learning will get it wrong every time. So don't expect me to get better at this than Netflix does, and don't expect me to get better at this than Spotify does. And you will get it wrong too if you start to implement this. But it doesn't matter very much, because machine learning is about the art of approximation. We're going to make a model of reality, and we're going to use that model to recommend items in this case. And in other times, if you want to detect spam email, you're going to make a model of a spam email and try to match that against incoming messages and see if that matches your model. And if it does, it's a spam email. But it will be wrong at some point. I will get back to this. First, let me show you what recommendations actually do, how it works. So, if you build a system like Netflix, you can see the 5 stars after the title of every movie. That's a rating you're giving, right? This is how much you like the movie. And based on that fact, I can learn the computer to show other movies that are similar to the one you watched and you liked. That's basically the idea what we're going to implement today. So if you look at a system that serves movies or songs for that matter, or maybe newspaper articles. I talked to a few guys this morning that were working on a newspaper website. It's interesting for them as well. And what you end up with is a large database that contains users on one end and items on the other end, and they get linked by ratings. But as you can see on my slide, it's very empty, right? Because you haven't watched every movie on Netflix. 35,000 movies. Who here has watched them? Nobody, right? And that's a problem for us. Because if you want to recommend a movie to someone, you want to show them the movies that they like best. And the only way to know for sure is to ask them to rate every freaking movie on the planet. That's the 100% solution. And that's why we can't solve this problem. It's unsolvable, basically. Let's be honest. I'm not going to rate every freaking movie on the planet. So the only other way to fix this is to predict what the other movies will be like. And some movies will be easy. If I consistently rate movies in the action genre with a 5 and romantic movies with a 1, it should be easy, right? But that's not always the case. There tend to be movies where there's partly romantic stuff going on, and the rest of the movie, 80%, is pure action, people shooting other people. And I still like that. My wife likes the more romantic movies, so that's also the reason why Netflix fails. If you use one account and 2 people, you get 2 profiles mixed together. Huh? That's weird. Because I like action movies better than I like romantic movies. But my wife is at home at the moment, and I heard this morning she watched a romantic movie last night, so my recommendations are messed up. So this gives you a sense of what is going on with machine learning, actually. We have to predict in certain situations what the answer will be, because we impossibly can't know what's going on. So what we're going to try to do today is we're going to fill in the blanks with predicted values. That's basically it. And here's a cool trick. I'm going to say I have 3 properties that describe me. And this is a random number, because it could be 10, could be 15. I don't know up front, but I'm going to choose one number. And that's 3, because I have 3 properties on my screen. Also, the next matrix in the middle is going to describe what the movies look like. And they also have 3 properties that describe them. And which properties are this? I don't know. That's also very weird, right? Because that's the second problem. First, I couldn't ask you to rate every movie on the planet. And the other thing, I couldn't ask every person that puts the movies on Netflix or puts the songs on Spotify to tag them. What's the percentage of action in this movie? What's the percentage of romantic stuff in this movie? What's the accent in the movie? Because I absolutely hate some accents, maybe. I don't know. I don't know why I'm giving a certain rating to a movie, so we're going to predict that as well. And this is getting tricky, right? First, I'm going to predict the ratings. Then, on top of that, I'm like, okay, how am I going to predict this? Oh, maybe I can describe a movie in certain properties, but I don't know which properties. So I'm going to choose a random number. I'm going to say this is the amount of properties that describes a movie. And the same thing for a user. So, and then, if I got that, then it's a simple multiplication of 2 matrices together. And people who've done math will find this easier than people that don't have this knowledge. But in the end, what we'll do is we'll say a rating of 5 is a multiplication of those 3 properties times 3 other properties from the user. And that's it. And we're going to ask the computer to come up with the numbers in the other 2 matrices. That's what we're doing when we're building recommendations. And it works like this. And there's a third randomized trick in this. I'm going to choose random numbers for the first matrix. Why? Because I can. And this is really true. Scientists have come up with this model. It's matrix factorization for people who like to Google and spend a whole 3 weeks reading a scientific paper that they absolutely don't understand. I've tried, trust me. It took me quite a long time to learn this. And they come up with this idea, okay, let's pick random numbers. And the next step, what I'm going to do is I'm going to ask the computer to execute a linear regression algorithm. And this is a sort of technical thing, to come up with the other numbers. So what I'm going to do is I'm going to use the first matrix with random numbers. And I'm going to choose a random number for the other values. And I'm going to try to minimize the difference between the predicted rating and the actual rating I have in my matrix. And the computer will take about 100,000 times to do this per rating. And then it will have filled in the other matrix. And that's about it. Then we have a predicted rating, but it's very, very wrong because it's random. The next step, I'm going to make this better. So what we're going to do is we're going back to the first matrix. We calculate the first one totally random, then the next one we optimized using machine learning. And then we're going back. We're going to wipe this matrix again, and we're going to ask the computer to run another round of linear regression and come up with better numbers for the first matrix. So in the end, what will happen is we will first optimize the first vector, then the second one, we go back to the first, second, first, second, first. And this is called the alternating least squares algorithm. Because the error rate between the predicted rating and the actual rating, we can calculate using a formula called least squares. And alternating comes back to the alternating between the two matrices that we're optimizing. In the end, after 20 attempts, we should be there. Somewhat. Weird, huh? I was kind of surprised by this. People pick random numbers, random number of factors, and they run 20 times and then, ta-da, it works. And trust me, this works. This really works. You can try this out yourself. I have the code on GitHub. You can download it and run your own ratings through it, and it will work. You will be surprised at how well this actually performs. It will get about 80% of the recommendations right. Pretty good for the fact that we're using random numbers. Apparently, it's true in this world that we can use chaos, randomness, to come up with a proper model for the reality. I find that very, very, very fun. So now that you've seen a little bit of the theory behind machine learning and you're probably all confused, anybody have a clue what's going on? How to do this? No, right? But do you need to know all this? Let's keep it at this. Let's keep in your mind that we're going to model a user, we're going to model an item, and we're going to match the two together. That's the idea behind this. That's basically what recommendations do. And you can build this algorithm using one line of code in Apache Spark. Apache Spark is a distributed computation engine. It does a number of things, but the most basic stuff is map-reduce algorithms. Is there anybody who has been to the session this morning on Apache Spark? There was one? No? Ooh, this is completely new to you then. So what it does is it's capable of running an algorithm across multiple machines, which provides scalability. And on top of that, it provides a wide range of standard libraries that you can use to execute common algorithms across those machines. And one of them is machine learning. And there's quite a few algorithms in there. I'm not going to list them. And the most important bit to keep in mind is that everything is in memory. So it's very fast. That's a good thing, I guess. So this is how it works. An Apache Spark program is a regular old Scala program, but with a small difference. What we're going to do in the program is we're going to set up a configuration for Spark, and we're going to say, dear Spark, I want to use the local master. This is my main thing where I'm going to send my program code to, and he will split it up across several machines. And between the square brackets, there's a star, and this is where it gets cool. If you put in a star, it will use every single core in your machine, and your laptop battery will drain in half an hour. It's a good battery test, and on top of that, it's very fast. The other thing I like to do is I like to send a app name for my Spark application, because if you run on your local machine, it will work. It's no problem. You can do this. You can start with a single development machine, and you can do everything. It will be slow, but okay. But once you submit this application to a Spark master on a different machine in a Spark cluster in your company, and 30 other developers are using the same machine, you will notice that each of these developers, when they forget this line of code, will get a GUID as an application name. good luck finding your code if it breaks. So I'd like to set this even on my development machine, and it will save you from a lot of trouble. The last line, and this is also something I learned from Scala developers. I'm normally a C# developer, so I like to use long variable names. Scala developers don't do such a thing. They do short names. Spark context SC is a new Spark context based on my configuration. Now that I have a Spark context, I can write a program. And I don't have to think about the fact that it has to be split up across multiple nodes. If I have multiple nodes, that is. All I need to do is I need to say, OK, dear Spark context, I want to use a text file, my comma-separated file. And I'd like to perform several mappings. I'm going to split each line of text on a comma and then convert it into a record type and then count them. And here's a cool trick with Spark. The first 3 lines of code on this slide will do absolutely nothing. If you run the program without the last line, nothing happens. It's very fast. It won't read the file even. And here's why. The mapping part is just a definition of what's going to happen on the Spark cluster. The count, in this case, is a reduce operation, which will fire off the mapping, which will split the data into several partitions, several sections of data, and send it off to a server for processing. So if you write your first Spark program and you're thinking, ooh, that's fast, then it's probably not working. And the other thing I noticed, the text file in this case could not exist, but it won't tell you until you run the count operation. That's also because it's not executing. And here's another cool thing. If you run on a cluster, then where is this file coming from? Anybody have any clue? If you're lucky, it comes from the master. Yeah, you don't know, basically. You specify a relative path, and that's it. So if you start to do this, please, please, please use HDFS or a SQL database or something that's network accessible for all your nodes in your Apache Spark cluster. Otherwise, you get all sorts of weird errors. This code is sent off to several nodes, and those nodes need the file on disk in the same folder as their working folder for the Spark installation. That probably won't happen, and it's very, very bad if you do such a thing. But yeah, that's what I learned from using Spark. So to get back to the whole master-slave thing, actually what will happen, your Scala code will be submitted to a Spark master, and that Spark master will be responsible for distributing the code across all the slaves. And once you start operations like count, it will automatically split up all your data in the most optimal version he can come up with, and it will send it off to the slaves for calculation, and the end result will get back. Counting lines of code is very simple in Spark. You wouldn't use it for that. And it will probably send it off to 1 or 2 nodes and then be done. If we're talking machine learning, it will be a lot more complex, and you will see very interesting timeline graphs on the master telling you what's happening. So this is how Spark basically works. Not too much fuss going about. I think that if you know Scala, Spark should be doable for most of you. Then let's go back to my recommender system. So I have a running system that's collecting ratings from users, and I'll store them in Cassandra. Obviously, you can use SQL Server if you like. And if you're running Netflix and you have 5 million plus users, you will end up with a broken SQL Server database. But if you're going to try this at home, use a SQL Server in your own company. Start small. Cassandra is a nightmare to maintain if you don't know what you're doing. And it's not worth the hassle in the beginning if you're just starting out with machine learning. So in this code, I'm asking the Spark context for a Cassandra table, which is in the recommendation database, in the ratings table. And I'm going to load a rating object containing a user ID, an item ID, and a rating, which is my first matrix. And it's very empty. It doesn't contain a whole lot of data. And then next, I'm going to define a couple of variables, which I'm going to use for training. And what will happen is alternating least squares, ALS for short, for Scala developers, and I'm going to say, train this model. And I'm going to put in all the ratings I have. And I'm going to say, OK, rank, in this case, is I have 10 properties. This is what I explained before with the two matrices. I'm going to train for 10 properties. And I'm going to alternate 10 times. This is the iteration parameter. And the last parameter I'm going to put in the lambda. This is the learning rate for my machine learning model. And this has to do with linear regression. It's going to decrease the error rate, try at least, by a factor 0.001. If you're interested in more details, I suggest you either Google it, or there's an excellent course on Coursera, a free machine learning course that explains all the linear regression stuff, and it's actually quite good, I think. And the end result will be a model, which is basically my first matrix I showed you on my slides, but then all the blank spots are filled in. And from this point on, it's basically order it by rating for each user and ask for the top 10. And that's it. So first I spend a lot of time explaining to you that I'm using random numbers. I'm using a lot of computing power, 100,000 iterations per rating. And then I'm, OK, this is all sorting and then selecting. That's it. And this is also one of those things that happens in machine learning. Training a model is very, very hard for the computer. It takes a long time. But using it is very, very fast, because the model is so simple. So if you're trying to build a machine learning solution yourself, and you're going to attempt this, be prepared to scale up for large amounts of data, but don't worry about too much about using the model, because it's fast. So now that I have a trained model, I'd like to use it in my application. And in good fashion, I like to make this reactive for maybe not so obvious reasons. The reason I'd like to make it reactive is because training the model is taking a long time. I'd like to run this on a background thread. Better yet, maybe on a different machine, so that my microservice can keep on running. So here's what I did. I made a central actor in my application that I can ask for recommendations and that I can tell, go train yourself. And the go train yourself command will fire off a second actor, which will run in the background, and he will keep track of the training process. He will talk to Apache Spark. And there's a number of ways in which you can do this. So if people have used Spark before and know about Spark streaming and actor streams and all that sort of stuff, I've chosen the most simple way to do this, and sorry if you feel different about it. Then, when the training is done, the recommender system will get a message back, I'm done, here's your new model. So this way, my main model will stay available for users while I'm training a new one. It's a good trick. And everything is exposed using Akka HTTP, because that combines very well with Akka. You could use other stuff, but yeah, I find this very useful. So this is basically the structure of my microservice that I'm using. Let's zoom in a little bit. So this is my recommender system actor. It has an optional model, which could be empty, because if you start the service the first time, the model is empty. It's not trained. And I like to express this in an option. Next, it accepts a few messages. So first, it's a train message, not the one on the table, but training, exercising. And the second one is generate recommendations. And I can generate recommendations specifically for a single user. And finally, it accepts a training result, which is the reply from my training actor. So I've shown you already how to train a model, which basically goes like this. It fires up the training actor. The training actor will call the als.train function and will send a reply back to the recommender system. So that's not very interesting to show you. This one is the missing piece in actually using my model. So I trained my model before. And when I ask for recommendations, it will go like this. If the model matches some model, which means I have a trained model, I will ask it to recommend products for a certain user ID and a number of items. I specified in my code earlier that it's 10 items. And what will happen is I will get back a set of items from the matrix I've trained, and I can map that to my own format so that I get rid of certain properties I don't need. And that's what I give back to the user. You see, it's one line to train it. There's one line to use it. I think, personally, that this is very basic. Actually, if you want to start using recommendations today, you don't need to learn everything about statistics. You don't need to learn about linear regression. You just need to know how to apply this. And trust me, everything is in the documentation of Apache Spark, and it's well explained how it works. And if you're unsure about things like lambdas and iterations, experimentation is your best friend. Oh, and in case my model isn't trained, I give back a nil, which is in Scala the thing for an empty list. So no model means no exception. It just means you don't get anything. So, okay, I've trained a model, I've integrated it, but how can you know for sure that it works? Anybody have any clue as to what I can do next to check this, if this works? Unit test, perhaps? Yeah? That's a good one. You can compare the new matrix with the original one. That's one method to do it. It's a very mathematical way to do it. Yeah, and it works. So the normal way to validate this sort of thing is to come up with a confusion matrix, they call this, in which you keep track of false positives and false negatives. And you calculate an accuracy and a thing called recall. It's all very scientific, and I've come up with a non-scientific way to solve this. So what I'd like to do in my system is this. When a user clicks an item, sorry, that's step 2, actually. Step 1 is, once you generate recommendations on your homepage, store the list of recommendations you generated, together with the timestamp. The next step, when a user clicks an item in your system, keep track of the fact that it clicked it. And here's why. If a user clicks an item, I'm going to assume that he likes the item. Whether that's true, I don't know. I can't see. But I'm going to be very binary about this. You either, if you clicked it, you liked it. If you don't click it, you don't like it. It's a representation of the reality. It's also machine learning, but very handwritten, so to speak. And the third step, I'm going to crunch a few numbers with this. And here's how that works. So if I clicked an item, interesting, and I showed it in the recommendations, this is a true positive, right? This makes sense, I think, at least. The second, if I didn't click it at all, and it was shown in the recommendations, this is false positive. This is not the stuff that I want to see. The other one is obviously, if I didn't show it to the user and he clicked it, it's a false negative. I absolutely should have shown it to the user. And the last one is, I didn't click it and I didn't show it. Good stuff. I don't want that. So here's what happens for me. I've got 4 items recommended to me. And this is a sort of simple scenario. The first one I like, Akka with Scala for Dummies. Yeah, it's interesting stuff. I read that one. I don't know if it's an existing book, but... The second one, Cooking with Your Grandmother. As fun as it sounds, I don't want to see it. And the third one, something about bears. I'm not a biologist, so I don't know. Why don't you remove this from the list? And the first and the last one, 1001 things you don't want to know about. Yeah, I want to know that. But sadly, although I did get 4 recommendations, there's one missing. Advanced Apache Spark. I use Apache Spark a lot, but I would like to learn more. But it didn't show it to me. Sad. Oh, bummer. Well, nonetheless, let's see what happens. Okay, so I've got 2 interesting recommendations. This is my first number on the right. The second one is 5, which is the items that are actually remaining in the database for me. And in total, I have 10 items. So that gives me a precision of 0.7. 70% accurate. Is this okay for you? Anybody? I think 70% is a bit on the low side, but yeah, well, it happens. And the next one is recall. This measure is about how many items from the set that is interesting for me are actually shown to me. Recall is sort of, it gets out of your memory into, you can use it. And in this case, only 2 items of the 3 that were interesting to me were actually shown, which is 66%, which is even worse. But here's the thing. This sounds, yeah, well, okay, it works, but yeah, not very well. And this is because there's a problem with this recommender system. And one of the problems is, if I want to increase the precision of my recommender system, I want to show more good recommendations, I have to reduce the number of items that I'm giving back. And why is that? Because if I show more items, there's a bigger chance that there are items that are not interesting to me. Right? But if I show less items, I can't reach a precision of 100%. I might reach it, but I probably don't. Because if I show only 1 item, it could be right, it could be wrong. So I could reach 100% or could reach 0%. That's not something you want, right? So what do? I increase the number of items I'm going to show to the user. And yeah, more items means lower precision. But it also means there are more interesting items coming back. I get a mix of uninteresting and interesting items, which might give the user more choice in what he can see. So when you're trying to build this yourself, then there's only one way to know for sure if your system works. Use this technique to record the numbers and monitor them. You can't write unit tests for machine learning solutions because it's an approximation. And the minute I train a model, it's wrong. Because the world changes. As soon as you save the model in a variable, someone will come along and give a new rating in your system, and then it's wrong again, because who knows what could happen. So the only way to optimize this properly is to first crunch the numbers, send it off to a dashboard, and watch it on the development room, and see if it suddenly drops or increases. And that's the moment where you want to start to debug this system, where you want to take a closer look and see, okay, why is this happening? Do I need to increase the number of properties maybe? Do I need to increase the number of iterations? Or do I need to decrease the number of iterations? And this is all experimentation. I'd love to say with all the scientists in the world that machine learning is awesome and it rules and it is really, really simple. It's not at all. And frankly, nobody knows how it works exactly. And that's not a problem as long as you take proper measures to use this. Make sure that you check it with the user. Make sure that you monitor your system so that you know when accuracy is going to drop, when it gets worse. So, yeah, with this, I'd like to invite you to try this out yourself. You can download every bit of code I've written from my GitHub account. And if you have questions, tweet me. I'm happy to help. And yeah, then I have time left for questions. Yeah. It's easier.
Can you show the implementation of the recommend products method? Because I noticed that you're not ordering by rating.
No, I don't do that. That's a good question. So can you show me the recommendation implementation and why is it not ordering?
It's not ordering when you extract the results there. Maybe it's ordered inside.
Yeah, it's ordered inside. So Apache Spark takes care of that. Actually, the recommend products method that I'm calling is on the model from Spark, and that will order everything for me. It's actually not ordered on the server. It will do that on the fly. So that's also an important thing to keep in mind. But it's very fast, so it's not a big problem. Yeah. Any other questions?
In your use case, would you always train the model on all the users in the system, or would you ever sort of pick out one user and then train for that user only?
You could incrementally train your model, but once in a while you have to train for everybody, and that's because one change in one movie could mean that it changes for everyone, and one change for a rating for a single user could mean that everyone else is touched by it, and this is because we have a very general concept of the number of properties that that describes a user and that describes an item. So, yeah, you could do it incrementally, but I would suggest that once every week or so, I would train a full set again. Yeah, and that's also a general tip on working with this sort of stuff. You have to retrain the model every once in a while, and how often that is depends on what you're doing and how well it goes. That's why I suggest you monitor it and then decide what you're going to do. Yeah.
I'm personally interested in the way the Spark actually communicates with the Akka actor Park. I mean, you compute this model and then you somehow store it persistently, or it stays somewhere on Spark? Or
Yeah, I made a sort of a shortcut there. I store it in memory at the moment. But what you could do is save the model on HDFS or on disk. You can do that. So, yeah, it's one line of code extra to do that. Yeah. Any more questions? I guess not. Cool. Thanks for listening.